I'd like to welcome our next speaker, Dr. Nils Andersson, Professor Nils Andersson. You ready to take the stage?
Yes, I am. Thank you very much. Actually, it would be better if I didn't use the mic. Does it work for you?
Yeah.
Because then I can run around and jump about and be crazy. Okay, so I'm here to talk to you about my new romance novel. Sorry, this is some other event, so I forget, okay? So I'm here to talk about this. Okay? It's a ball of iron, or steel in a way, but this is iron. Okay, where does it come from? It comes from stars. Okay, so stars burn material from hydrogen to helium to heavier and heavier material up to iron, and then it stops. Okay? It stops because iron is a very stable isotope. It's very difficult, costs a lot of energy to go beyond iron. So stars are really good at building iron. But we know there's more. So where does the rest come from?
Supernova.
Don't get the punchline, just because she told you. What was that? No t-shirt for you. And anyway, if someone calls out bingo, I've got this, you should be very, very afraid. That goes back in my pocket. Okay, so what I'm going to talk about is a little bit about the iron, to start with. And the question I'm interested in is, how big can you make this ball of iron inside a star? Okay? And I'd like to start with a quote. So here's a quote from Arthur Eddington, who some of you might know the name of. So he was instrumental in popularizing Albert Einstein's theory of gravity. He was he was part of the experiment that detected the predicted light bending in 1919. And then he was also part to a controversy, which is what I'd like to talk about. So he said that what you do as a physicist, is at least a mathematical physicist, you calculate according to the theories of physics that you know, and then you ask your friend with a telescope, so that's Mike over there, to go and stare into the skies and see if you can see anything that you've calculated. So what about this ball of iron? So let me tell you about one of my heroes. So here he is. It's Chandrasekhar, won the Nobel Prize in Physics in the 1980s, many years after he did the work. So as a young student, 19 years old, he boarded the boat in India to sail to the UK to go to Cambridge University. And on the journey, he calculated what would happen to a ball of iron in a star if he kept on building it bigger and bigger. And so to do that, he combined Albert Einstein's theory of gravity, which is what Emma talked about, with quantum physics, which was fashionable at the time. And he found, to his surprise, that you could not build balls of iron in stars bigger than a certain size. If it was heavier than something like 1.5 times the sun, it would have to collapse and fall in on itself. And that was a huge problem because at that point astronomers believed that all stars ended as what we call white dwarfs, which are just they just fizzle away and that's it. With this big ball of iron in the middle. But now this young guy who wasn't even a proper student, right? Because he hadn't been to Cambridge yet, calculated that that couldn't be true. If you kept on building this iron, it would have to fall in on itself. So what happened was, he came to Cambridge, he talked to people about this thing, and Arthur Eddington told him that was complete nonsense. He should just shut up and go away. Okay? So he started a controversy that eventually led to Chandra leaving the UK and going to the US. And it took about 50 years for this idea to give him the Nobel Prize. Okay? So what he calculated was the fact that you cannot build these balls of iron to arbitrary size. Something has to happen. So now we're led to ask, what happens if you give me superhuman strength and I start squeezing this ball? What happens as it starts falling in on itself? Okay? Suppose I squeeze and I squeeze, what happens? Why is it a ball of iron? Well, that's because the electrons of the atoms are pushed up against one another. Okay? But suppose I am really superhuman, of course, you can tell. I'm a feeble old man, so it's not going to happen. But suppose I had superhuman strength, I keep on pushing, what's going to happen? I push through the electrons.
Release energy.
I will release energy, that's correct, and then I will keep on pushing. And then what happens? Well, at some point, the nuclei of each atom is going to come into touch. Okay? So that can stop me from pushing. But when Chandra did the calculation, people didn't really understand how the atomic nuclei work because the neutron hadn't been discovered. So that was not the starter. So you keep on pushing and eventually you form a black hole, but black holes were really controversial and were not understood until the 1960s, so that was not the solution either. So it caused a huge problem. Okay? The answer to the real problem is that there's no real issue there. You keep on pushing, you get what we call a neutron star. When the nuclei start touching, you have a much smaller star, which is mainly made out of neutrons, and is held up by the fact that the neutrons push up against one another. Okay? So that's in a nutshell what the neutron star is and how the story of neutron stars come about. And then there's another aspect to it, which says that the moment the neutron was discovered in 1932, people immediately said, let's make stars out of this thing, of course! Because that's the way us theoretical physicists work. You know, give us something to play with and we're going to make a star out of it. Don't worry about it. So, do these things exist? Well, of course they do. In fact, we should have known already from 1,000 years ago, give or take, because we see the remnants of explosions of stars. We see supernova remnants. So what happens in a supernova is a star runs out of fuel, it can't burn anymore, so basically it starts falling in on itself when this iron core is too heavy, and then there's an explosion when this material bounces. We see the explosion, and what's left over sometimes are these beautiful supernova remnants. Okay? And so, in this case, this is the Crab Nebula. In the middle of this sits a neutron star. Of course, they didn't know that. When the Chinese astrologers, as it were, made records of this in 1054, they didn't know there was a neutron star in there because the neutron hadn't been discovered, remember? Anyway, fast forward to one of my early birthdays, 1967, when Jocelyn Bell Burnell was looking through the data from her new radio telescope in Cambridge, a young PhD student, and she found little fuzzy bits. Every now and then there was a little fuzz in the signal, and she thought, I'll discard that, that must be nonsense. Kept on looking for quasars, which are bright galaxies. And then eventually she realized that this little fuzz came back whenever, basically the same time of day over and over. So when the telescope was pointing a certain direction, she saw the same little thing over and over. So maybe it could be something. Indeed, it was something. She discovered the first pulsar, and pulsars are rotating neutron stars. So the story is quite simple, although we have no idea how it works. There you go. So a pulsar is a rotating star made out of neutrons, essentially, with a very strong magnetic field, and it pulses, as we see it, because the magnetic field is misaligned with respect to the rotation. It rotates like this, magnetic field is tilted, and then you get emission of particles along the magnetic field axis. So every time this thing sweeps across the sky, passes the telescope goes beep. Okay? That's essentially what's going on. And so since the 1960s, when Jocelyn made the first discovery, we've seen about 2,500 of these guys. And it's a little bit like zoology. They are like people. They have their own characteristics and their own behavior. And our job is to try to understand how they work and why they do what they do, and then try to piece together the observations with that quote from Eddington from the beginning. How does this fit with our understanding of physics? And so, unfortunately, I should come clean. This is a nice cartoon, but we really don't know how this works. There is no theory on the market that can calculate for you how this emission actually happens. So we know a lot, but there's a lot of things we don't know. So let me go into a little bit about what it is we're trying to do. So basically, here's another quote. So what happens if you take this matter and you squeeze it down to neutron star size? Take this ball again and squeeze it. So the atoms squeezed away, get to the nuclei, they touch. How heavy is this thing? Emma said a neutron star is the size of Southampton, something like that. It's about 10 kilometers in radius. weighs about 1.5 times as much as the sun. What does that mean? Well, it's Neil deGrasse Tyson's take on it. 50 million elephants in the volume of a thimble. You can try that at home if you can get access to 50 million elephants, but you know, it could be, it's not the best pet, I think, maybe elephants, and 50 million elephants is rather a lot, but you know, maybe. The bottom line is, the real question here is, what happens to those laws of physics according to which I, as a mathematician in my day job, should calculate? What happens? Okay. I know my everyday physics, but what happens to physics if I squeeze into these 50 million elephants of size? What happens? So the story is very complicated. So here's my version of it. The story is very complicated because I have to take all the physics that we know, more or less, and mix it up together. I need to understand gravity. As Emma explained, these things are heavy and they're very small, so the gravitational field is really strong. Gravity means I have to understand Einstein's theory of gravity. I need to understand gravitational waves and so on. I need to understand electromagnetism because these guys are rotating magnets. Right? So I need to understand how gravity and electromagnetism communicate. How do they work together? Okay? Otherwise, I wouldn't know why these pulsars pulse. Well, I told you I don't, but okay. We need to understand what they're made of. So that brings in the kind of physics that people probe the Large Hadron Collider. We need to understand what happens when I squeeze matter this much. And that brings into play the two aspects of particle physics. The strong interaction, which decides here what are these guys made of? How many neutrons, protons and electrons mainly do I have? Right? So how many electrons and protons per neutron do I have? That's what I need to understand. And then these stars are a little bit like people. They age. They age by cooling. They're born hot, but they cool. They slow down because they lose energy through this emission. So they evolve. Mainly due to the emission of neutrinos. Another part of particle physics related to something called the weak interaction. So basically, this is all of physics. And it gets worse because these stars are really cold at 10 million Kelvin. They're really cold on the nuclear physics temperature scale, which says that, you know, a million Kelvin is hot, but 10 million Kelvin is really cold. And that means that they are, because they have charged particles, they are superconductors, and because they got neutral particles, the neutrons, they're also superfluids. So this is all of physics. Okay? It's all of physics in a ball that you put together and you need to stir it and say, this is why it does what it does. The problem is, we don't really understand these different pieces of physics. And my job is to understand them all together. So, you know, there are two ways of looking at this. One is the optimist view, which is this is great, there are many great questions to work on. The other one is the defeatist point of view and say, what's the point? And some days it's like that. But mostly it is not. And here's one reason why it is not. Gravitational waves. Okay? So as Emma said, Albert Einstein came up with the idea of gravitational waves in 1916. 1 year after he finished his theory, he realized that this theory predicted gravitational waves. And he realized that whenever gravity changes, you would get gravitational waves. So in particular, if you've got two stars that go around one another, then gravity changes, right? Clearly, because you know the position of these guys changes, the gravity changes, there will be gravitational waves. Okay? And then he realized that he didn't really believe in this. Because it turned out that you could, by some mathematical trickery, you could make these waves go away. And then people like Eddington didn't really help. Eddington famously said that gravitational waves propagate at the speed of thought, basically saying they're just rubbish. And so people were confused. And the reason why people were confused is that gravity is a tidal theory where you have to measure relative distances. And what people were obsessed with were trying to measure these waves at a point. But you can't do that. And so there was loads of confusion until the 1960s. In fact, Albert Einstein himself famously wrote a research paper in the 1930s where he proved that gravitational waves could not possibly exist. Okay? And then he was sent, as we are, the criticism by a peer reviewer that pointed out to him that he had made a mistake. Upon which Albert Einstein wrote back to the editor of the journal saying, you know, I didn't send you this paper. He probably said it in German, but I can't really do that. So he said, you know, I didn't send you this paper to show to someone. I sent it to you to publish. And then he probably thought about it a little bit and he realized that he had made a mistake. So together with one of his colleagues, he worked it through it, and then he said, oh yes, no, gravitational waves definitely exist. And then he changed his mind again. The final version of this paper says, gravitational waves maybe exist. So that was about 20 years after his first suggestion. So you can see, people were really confused. And then there was a breakthrough. In the 1970s, 1974 to be precise, Russell Holtz, another student, and Joe Taylor were looking at data from the Arecibo radio telescope, and they found a signal from what seemed like a double neutron star system. So being, inventive and imaginative, they called it the binary pulsar, because there's two of them. We also have a system called the double pulsar, to be really, but let's not talk about that now. And what they did was they figured out how to calculate how much the orbit of this system should shrink due to the emission of gravitational waves. So basically, as they go around one another, they lose energy, and they fall ever so slowly towards one another. Okay? And they worked out how fast would they fall towards one another, and then they compared to Einstein's theory. Actually, they asked some people who understood Einstein's theory to calculate for them how it worked, but that's not part of the story, really. And then they found, tracking this for some time, that the theory was really good. And so now, after some 50 years of tracking this system, we know that Einstein's theory, the prediction of gravitational waves, is good to better than 1%. And that's pretty good for a physics theory. It's pretty good for a physics theory that was made out of the human mind. It was not based on some sort of, here's my experiment, here's my this. It was a construction of Albert Einstein's mind. Okay? So that is really spectacularly good. So here's the gist of my entire thing, really. What happens if we zoom forward? What happens eventually as these two stars get closer and closer? Bang! You've got it. So if we were to wait, in this case, about 200 million years, yeah, that's the problem, isn't it? Yes. It's kind of good. I said, what do you do for your research? Well, I'm waiting for the binary pulsar to collide. Just keep on paying me, and that's fine. I'll just lift my salary and put my feet up. 200 million years should be a doddle, really. Eventually. But no, that's not. Anyway, so 200 million years, and these two stars will come together, and then what happens? So Emma talked about trying to find the gravitational waves, but how do we find these very weak, faint gravitational waves amongst all that noise, the people, phones ringing, people walking about, just clouds being a general nuisance, tides? How do we do it? Well, the answer is we have to try to use the theory. We calculate according to the rules that we know to predict what we should be looking for. Okay? But I already told you that we don't know how to do it because there's too much physics. So we do our best, which is whatever it is. Okay? And so in this game, what you have to do is you have to put all that physics on the supercomputer and try to predict, as the stars get very close and they crash together, what is that physics going to do? Okay? So that's what we would like to do. I'm going to show you a little movie because I'm very pleased with it. So this is done by one of our researchers here. It is a little movie of two neutron stars coming together and then matter sloshing about a bit, some waves, some red wispy waves coming out. In this case, it's just the densities that the wispy waves essentially are the gravitational waves. That's it. Doesn't get more exciting than that. 3 months of supercomputing simulation. It's incredibly exciting. Yeah, and quite a lot of storage of data, and quite a lot of swearing. Sorry, I'm not allowed to say that, but you know. And then you imagine, if you're in this business, you don't know the physics you're putting in, so you need to try many different things. This is very, very expensive, right? So you need to be a little bit lucky. You don't want to push this button, say, on this simulation and say, look, 3 months from now, I'm going to come back and check if it worked, and then you find out you made a little mistake, and then you have to do it again. You can see why PhD students get a little bit, how many times do I have to run this thing before I can actually finish?
And you can't prove it.
And you can't prove anything, so then it ends up just making it up, really, but okay. So this is where we are. We'd like to put all that physics into these simulations. And we're quite good at this, I think. But the reality is we can never do it. It would be way too expensive. So we know actually the physics better than we would ever be able to do the simulations. So all we need are bigger computers, people. So more money, okay? There will be a donation box out there. No, actually, the real story is we have to be smarter. I think we're getting very close to the end of what is possible with the computing technology that we have been using since the 1970s. Now, if we want to make a big leap, we need to think outside the box. But I think, to be honest, people like me, old people, probably won't do it. We need clever young people that come in from left field saying, oh, the algorithm from Snapchat, whatever, is going to do this. And you think, really? I've never heard of this Snap thing you're talking about, And that's probably how it's going to happen. There's going to be some breakthrough because some young person that doesn't have the bias that all of those of us that have been in this business for a long time have, is going to figure out something that we couldn't do. But we're up against the physics and the computing, so it's kind of tough. But then again, sometimes in life you get lucky. So it was predicted that we were going to see one of these neutron-star collisions maybe in 20 years' time or something, together with an electromagnetic signal. But then, August last year, gravitational wave chirp, followed by a gamma ray burst, less than 2 seconds after, so a big flash of gamma rays picked up by orbiting satellites, and then minutes, hours, days, weeks after, the whole spectrum of electromagnetic emission. An event that was tracked by Mike and about a fifth of the planet's astronomers, together with the 2,000 people in the LIGO scientific collaboration. So this is the biggest conspiracy theory ever. If you want to make this not happen, you have to involve, I don't know how many people, how many astronomers on the planet do you think? So, you have to make some 20,000 people keep this secret. That's pretty tough. They have, 20,000 people is a lot of bribes. Okay, so that's it. This is what Mike's going to talk about, so I'm not going to touch it. The short story is, just a couple of months before this, I was at a panel with one of the experts that then ended up leading one of these observations, and we agreed that this was just not going to happen. So it looks bad for us, I think. But this was an example of how LIGO stands for lucky. Because this event, this neutron-star merger, was much closer to us than any other gamma ray explosion, etc. that we see, much closer. So these events like these will be very, very rare. And so sometimes in science, you have to be lucky. And this is an example. The first time we saw this, we were incredibly lucky. The first time that we saw black holes crashing together, like Emma showed you, we were very lucky because that signal was extremely strong. And you can ask, after 100 years of trying to catch gravitational waves, what would happen if we hadn't been quite so lucky? We'd be this little fuzz, that we may or may not be there. then all this, nervousness about, is it or isn't it? That sort of thing could come into play. But here, we were very lucky. So LIGO has been lucky twice. I think that's unfair, really. And all I need is a big computer. But there you go. Okay. So this is the end. We now know not just where this infernal ball of iron comes from. We know where the heavy elements come from. We know that they probably are not made in exploding stars, things like gold, platinum. But this event, this one single event, pretty much predicts that we can make all the gold, all the platinum, all the heavy elements. And I think it's a really nice thought. Every single piece of gold and so on that we have comes from the collision of two dead stars. I think that's a really nice thought. And so thank you very much.
Sorry.
Yeah, switch it on. That's all. It's,
I mean,
Yeah.
Thank you so much. What an amazing presentation. Does anyone have any questions? Yeah.
So you talked about some fairly extreme events like colliding black holes and colliding neutron stars. What kind of event would have to happen for you to try and look for deviations from relativity, so sort of quantum deviations?
Okay, so this is a deep question. He's a deep thinker. It's a deep question because we know, I talked about how accurate Albert Einstein's theory is. Right? It predicts these things, but we know it's wrong. We know it's wrong because we cannot marry general relativity to quantum physics. So we know that if we go to the very small scales, general relativity is wrong. And we know that it could be wrong because we can't explain what happens on the large scales in cosmology. Okay? So in cosmology, we have this theory that the universe was born in the Big Bang. That's pretty solid. But now we think that the expansion of the universe is accelerating. So it's accelerating faster and faster. And the explanation for this acceleration is something we call dark energy. It's a bit Star Wars kind of, sci-fi. Now the problem is this dark energy is about 70% of the energy in the universe. Okay? The stuff we see is some 5%. Then there's about 20% that we don't see that we call dark matter. We don't see it, we don't know what it is exactly, but we have some ideas. And it has to be there because of gravitational lensing and so on. And then there's this 70% dark energy that we need for the universe to accelerate. And we have no idea what it is. When people try to calculate what this dark energy could be, they go wrong by 10 to the power of some 120. That's one with 120 zeros after it. No one has ever been more wrong in the history of science than people that try to calculate the dark energy. Okay? This is one of our greatest successes. And so, this is a great question. And therefore, there is a minor industry in people trying to predict alternative theories of gravity. So there are two reasons, I think. One is everyone would like to bring Einstein down because he's so smug. Right? And the other one is we know it's wrong, so we need to try to figure it out. With gravitational waves, we can make some progress towards this, but some of the ideas that are bandied about right now are probably a little bit too outrageous. And we really do need these experiments to get a little bit more precise. So, for example, a space detector, LISA, will help. And then there's a possibility that we'll never get there, because here there really is a limit. You cannot expect to do better. So we can probably predict now what's the best gravitational wave detector we will ever be able to build, no matter how much money you give me. Right? So even if we have this collection, and even if you're all super billionaires, right, we're not going to be able to do it. So I think this is one of the big questions, and we'll see. Maybe next year's Pint of Science. Who knows?
Okay, so we've got time for a couple more questions, so if anyone's got anything to... Yes?
Okay, so you said that the pulsars, they're phosphors of electromagnetism, but it's made of neutrons. Where does the charge come from?
Great question. So they're made of neutrons, but not only. There's a few protons and electrons and maybe some other funky stuff that we call hyperons and whatnot thrown in. Okay? And so they have a magnetic field because they're born in a dying star. The star has a magnetic field. So as the star collapses, this magnetic field is frozen in. So they have magnetic fields. They are rotating magnets. Now, one of my other hobbies is to try to understand what this magnetic field is and how it works when you've got this mixture of physics, superconductors and so on. And the truth there is I'm doing just as bad a job of that as that other thing. So we don't know that either. We cannot calculate the kind of magnetic fields we believe you need for the phenomena that we observe. And it's worse than that because the fields that we can calculate are not stable, so they could not last. So this is kind of another disaster of science. That's my role. I do work that doesn't work. But I get paid, so that's okay. And I have to wait for 200 million years. So no, so there's some really hard questions there. But I think it's really only the case that because we are not able to put all the physics in, there's some ingredient that we're missing. And one day, again, some young person is going to come along, spend some time, not 200 million years, and they're going to nail that problem. But it has been with us since the 1960s. So these are big science problems. Because it's hard. And we're a little bit slow.
I mean, it's not that bad though. Like,
no, you're right. It's because we get paid.
yeah, and also because there are things that we'll never be able to kind of figure out. Like,
really,
we'll never be able to figure out how the world ends because when the world ends, the world will have ended, and we won't be there anymore because the world will have ended. So,
but you're missing something, right? Because in the multiverse theory, there will be another world that keeps going. And so in that one, we can...
yeah, it'll be like our identical clones that kind of figure it out rather than...
That's right, see?
But thank you so much. We're going to take another break. Can I have a round of applause for...